So, thank you first of all for the nice template. Unfortunately, I was not aware that it exists, so I may not answer exactly the questions that you have all answered in these nice presentations. So we are in a bit of restructuring. So as you all know, everything began in reality with the joke by Angela Merkel 2 years ago about the key technologies. And we are actually in the process at HZB to move from energy into the new research field of information. And material science has been identified as something that is also a bit scattered around in Helmholtz, and as I understood, in the information research field, that will be an area where the interdependence of materials research and information in one direction and the other direction will be situated. And yeah, and the Management Board of Key Technologies has nicely set up this structure, and we will contribute to the quantum materials um, in the sense of basic research, but also in the sense of contributing to the development of the devices. The structure at HZB looks like this: that we have a large scale facility, the synchrotron radiation source, so we are automatically in matter. Um, we are we have been in the Future Information Technology program together with Jülich so far, which was in our case in energy, and we will move to information as a new. We are in the process of establishing a new division, which will be called probably something like quantum and functional materials. In addition, we plan to contribute to the virtual materials design joint lab in this. And the people who come either from the energy, from the future information technology, or have not been there in the previous talk area, or move from other fields of energy are these people, and I want to present their research for 6 people in 6 slides. So the first activity is an activity by Bella Lake, who is also here, and Johannes Reuter, which excels by the close interconnection between material growth, material advanced investigation and experiment, and advanced theory. And one of the materials they are studying are spin liquids, because spin liquids are materials that are very new materials, which have, in the context of quantum technologies, the possibility to hold excitations that are non-abelian. And in principle, according to my understanding, you can mimic something like a braiding of a Majorana fermion in such a material. In the future, they will extend to other materials, to 3D spin liquids. They will create excitations in these spin liquids and try to control these excitations. Another activity within this field is high temperature superconductivity and multiferroic materials, which also contribute to IT research. In my department, we do band structure measurement with the RPES, with the RPES method at the synchrotron. So we have a focus on spin-dependent phenomena, and especially on topological insulators and the topological materials. We are functionalizing, so we connect the topological materials with other phenomena, which is first of all magnetism, but also superconductivity and strain. And in strain, we will collaborate in-house with a new department for functional oxide. In this context of the quantum technology, the magnetic topological insulators are, in my view, the most interesting because of the possibility to create lossless edge states that can be they can form interconnects in conventional computation, but also there are proposals for qubits where we need magnetic topological insulators. So that would be our contribution. We have a focus on ultra-fast phenomena. This has to do with our light source, with the use of stimuli to manipulate material. And in this framework, we generate spin currents. We investigate their decay channels. We also It will extend to looks at photovoltaic materials, may not be interesting for quantum technology. We do topological materials in real space as well. The word skyrmion was already dropped before, so we create these skyrmions with optical light with ultra-fast excitation. Study them. We have another focus on 2D materials, which comes from historically from the graphene, the other big flagship project. So we are heading towards the attempt to make graphene, to create high-T superconductivity in graphene. This is a flat band formation, which we then other 2D materials are these blue phosphorus, a new material that has a large band gap. That many of these 2D materials are potentially important for optical technologies. And for this, our own agenda is to create nano-scale angular photo emission, so nano-scale band structure measurement, which also, in my view, can be useful to investigate devices. So if you have a device and you can resolve this at 15 nanometer, you can study bending effect in existing devices. So we have several experimental methods at the synchrotron that are helping. The Department for Transport Phenomena is doing basic research on electronic and phononic transport. The phononic transport is studied by neutron scattering, by X-ray scattering for, first of all, material structure, then for the phononic structure. The aim could be to enhance the phononic transport or to reduce the phononic transport. At the moment, the thermoelectric materials are very important, and to reduce the thermal transport, this can be done with different strategies, increasing the harmonicity of the lattice, or to put atoms in cages and to scatter phonons. One example here is the mesoporous silicon, where the length scale of these pores has been adjusted so that they are between the mean free path of the phonons and of the electrons, and they can reduce the very strongly. They also operate resonant inelastic X-ray scattering, which is important investigation method. They will also study connection with oxides, material electron. And the Department for Oxides, Functional Oxides, did not exist until 2 years ago. This is our department, which is actually closest to industry applications. Catherine Dubourdieu is an expert on growth of functional ferroelectric and multifluoric materials, especially on silicon. That's something certainly for the industry application. She also does transparent oxides, and she produces the dielectrics that are part of the memristive device research in Jülich, and she does CMS compatible devices, and there are interactions. So the last slide, would that we don't have the template, otherwise you would not see this. Such a slide can only come from a young investigator. So Annika Bande, she moves from energy to us. She does theoretical chemistry, and the theoretical chemistry methods are in some sense automatically, so for her it's very easy to do time resolved investigations down to the femtosecond scale. And among her research, most important in the present context is that she does intercoulombic decay investigation in quantum dots, and also intercoulombic electron capture, which understood is more important for the molecule, so she can do both the molecule and the quantum dot, but also apparently for quantum dots. And asking her what she will be doing in 10 years, she said she will, in the agenda of the theoretical methods, the inclusion of the nucleus will be a task to do, and possibly also to include the nuclear spin for quantum. Yeah, with this, thank you for your attention.
Yeah, thank you very much. Comments or questions?
For comment, there's a highly relevant but very specific connection for the high thermal oxidation materials.
Good, good. Yeah. I was hoping that this.
We have expertise, but it's not ourselves.
Yeah, fantastic. When we came it.
Maybe I can ask the same question that we asked before. Do you see something which is missing in the structure that we have been discussing until now? Of course, we have here, I see that we are moving towards extending towards quantum materials. Yeah, so a lot of what we are doing is relevant there. Do you see other aspects that would be missing or that you would like to add?
Yes. Yes, I mean, of course, we are coming from the spectroscopy. For us, we study material up to a certain point. Now we also modify the material. We try to stay on track. Then comes a new material. Of course, we would like to contribute to processing these materials into devices. And I see this mainly the chance with English together, where we have already know each other very well. For other materials, if I should become very specific, ferromagnetic oxide, so one would in principle need insulating magnets with high Tc to make these, to create these topological qubits at room temperature even, and then we would, for example, think that in Rossendorf, the people who do spin waves are experts on such insulating ferromagnets. Would exchange them.
The presentation was very nice in the different groups, and we all know how excellent the science is that the people you went through are. And what you have now said for this question already partly answers my question, if you have a focus, if you want to go for something, and there you said you want to partner with either or the other center. But still, I would like to ask the question, how is it reflected in the Berlin strategy, this quantum information subject? It's quite difficult for me to see, how the center as a whole sees this subject.
Well, you know that we have a designated
scientific director. I know it is connected, but I never heard somebody saying, this is we have three areas, and that's one we go ahead and we focus on this or that, using our characterization methods with Bessie and with the neutron, as long as they are there. So for me, it's hard to judge, what is the status of that, or how is it promoted in the future.
Yeah, I can explain why. Because we are at the moment within energy. We are in a division together with energy materials research, which is very diverse, and the future information technology, that you know. And now we will focus much more on this. If you ask me how many PIs are working on this, then I could probably answer this. Or if you want to know if the people would be willing to drop other things and go more into quantum technology, this could also be discussed.
So I could even say it the other way around. I could imagine that this process here could be highly beneficial for you at HZB to make this subject, one of the selling points you have.
Yes.
So I missed your comment about the new director. So where was that going?
Yeah, and HZB has so far one scientific director, and we will in the future have two scientific directors. And our activities are practically in between the research, the responsibilities of these two directors. So
that's why I was asking, as you know.
Okay,
I would not know who to ask
answer
now. For what is
Sorry?
Yeah, I would not now today who of the two to ask about the importance of quantum technologies at the HZB.
May I ask what are the fields, what are the fields, the areas of these two?
Energy and large-scale facility. Okay, I think that I know where we belong.
this situation has certain risks, but also many opportunities. And we can use that vacuum to place the subject.
No, I mean, we could have asked them beforehand. Maybe one of them would have even come and joined because I think they believe it is very important. But at the moment, we're just try to contribute. If a certain dedication is required, we can.
So what I hear is, I mean, depending on the shape it takes what we are doing here, there might be some sort of high-level endorsement of this from the directorship of the HTT.
Yes. Yeah. No, the endorsement is fully there that we will go in information. We will stay with Jülich. We are very happy to join Karlsruhe, and we will be also very happy to stay with Ossendorf. We have also many contacts, and also with DLR. So the big point was that we will go into the third Helmholtz research field, which is information, and this was for us the important step, and the rest.
Excellent.
I'd be kind of relating back to my earlier question. I'd be curious to how what fraction of the application potential, any time scale, very long term, short term, of your quantum materials research, factor center, focus of the center, will likely pay into real superpositions and dynamics, basically systems, and what part will go more into other storage, energy materials, conventional classical spintronics, or so. What I was asking is, what fraction of the materials research will contribute, is likely to contribute in the application side to real narrow quantum technology? Getting at this more storage or will it be more appropriate to say there are quantum materials which are basically similar in quantum technology that contribute to quantum effects at the heart, but contribute to many other technologies?
I think the latter is the case. Yeah.
Well, beyond the scope, so far we have not identified what would be the physical quantum.
So if there's no other questions, let's move to the next talk. This would be
Yeah, okay. I'm from Dresden-Rossendorf, Jochen Rosnitzer, and I will give some overview what we're doing. We are mainly focusing really on materials again, so just in very similar like KIT, I would say, and Berlin. And I will just first show you a little bit about the structure. It's HZER and the main players there. And I think what was missing so far is the large-scale facilities, which is something which is unique for Helmholtz and which we should certainly focus also that is an important asset that we have. So what we have is more or less 3 user facilities. That's the Ion Beam Center, the Elbe Accelerator, and the High Magnetic Field Laboratory, where I'm from. And that is connected to 3 institutes, which are written here. So these 3 institutes are, each of them is running one of the machines, the user machine. And to give very brief topics which we are doing, let's say that institute is doing matter under extreme conditions, which means plasma. They're also using lasers for doing that. But the main players I'm talking about today is these material players which are here, the Ion Beam Center at HLD, and there's, for example, magnetic information technology, nanoscience, ultrafast spectroscopy. That's just giving some kind of overview of what's been done in the Ion Beam Center, or in the Institute of Ion Beam Physics and Materials Research. And HLD is doing mainly fundamental electronic we are embedded, we're doing matter research, so we're embedded in the Forschungsbereich matter, of course, and that is just one slide to see that is our cooperation partners already now, because in the matter area, and especially in the program for matter to materials and life, there are 7 Helmholtz Center and 1 Helmholtz Institute, and you see all the players are also in the room, plus additional ones. And we have cooperations. And once again, the main thing here is that we have this large-scale facilities which are doing research on with photons, neutrons, and we are doing it in Dresden-Rossendorf, ions, and highest electromagnetic. Go into details. This is more the general things which is done in this program. Then I start with the more fundamental things. That's the reason why I start with my institute first. Sorry for that. Thomas Hermannsdorfer is in the audience also, and myself. We are doing research, doing it in high magnetic fields, almost up to 100 Tesla. And you heard already about that. We have a great cooperation with Berlin, actually with Bella Lake, for example, also, and doing research on frustrated magnetic materials. We are also a member of a European facility, which is European Magnetic Field Laboratory. So we have also international cooperations in here in this high field business. And we are embedded in the Sonderforschungsbereich 1143, which was just evaluated for the second round, which is doing correlated magnetism, which is this kind of frustrated magnetism and topology. And we also, you heard before, also excellent cluster together with the University of Würzburg. We have this excellent cluster of complexity and topology in quantum matter. So that shows our cooperation, and in principle, that is, let's say, this on this end is a little bit the vision where to go in the end. The moment, of course, we investigate the basic properties of materials. Of course, we want to have in the end also general classification of that, and then here we stop at identifying possibilities for functionalities. That's really basic things, and say, okay, here's something which may be applicable for the future. But of course, there's also then in the Institute of Ion Beam Physics a more device-oriented approach. So here for the Ion Beam Center, which is Stefan Fatschko, who's the main responsible now for that, the idea is doing really single electron and single atom devices. So that means using low energy ion irradiation, for example, it may be possible to really implant one atom at one position in the end, and to really fabricate new devices, single ion effects on surfaces or 2D material, for example. And that is really to localize the atoms on the spot on the real side. Of course, that is a long-term vision, and that you have a deterministic ion implantation in the end. But that may be very important, of course, for some devices that you need, that you can use then later for quantum computation, for example. The next thing is, let's say, Helmut Schultheiss is in the audience. I mention only the people who are in the audience. It's a large group doing spintronics and magnonics, which means they find also ways not to use electronic transport, which is dissipation and large energy consumption, so to have something less with less energy consumption, just having the spin-based information technology, for example. And there are also, of course, you have to guide and to detect the magnons in the end, and all these steps are developed in this group. And of course, it would be nice in the end to have wireless transmission at terrestrial frequencies with this approach. The next thing is really the work done by Manfred Helm and co-workers, Harald Schneider here. They're trying to make semiconductor-based quantum devices. That means they won't really go from single photon physics to entangled photon pairs. That means they want to grow, or they're already growing, devices which are emitters, photonic emitters on 3, 5, in this case 5 is SN semiconductor nanowires, and then if you strain them, you can get some some kind of changing in wavelengths, for example, so strained quantum dots that is known to work quite nicely. So that might be a source of single photons and entangled photon gas, depending on the wavelength. And the idea is then to minimize these structures and to get then also maybe to manipulate them by a piezoelectric field, and then in the end to get really on-chip quantum sources, photonic quantum sources that is. And as I said, in the end, the long-term goal here is having entangled photon. Then finally, it's Georgi Astakov is also in the audience. That is really now building application devices maybe up to room temperature. Also before that was some application maybe up to room temperature in the end finally. And that is putting spin defects, here in this case in silicon carbide. So really having a vacancy in this compound and manipulating that. Again, the idea is using our large-scale facilities, the Ion Beam Center for making these devices. And I forgot to mention before, of course, analyzing these devices with our large-scale facilities, as for example, Bessie or Daisy or Newton scattering facilities and so on. And then, of course, in the end, that you have single photon emitters here also, and maybe in the end also to have some room temperature working devices that you can use later also for this quantum technologies. And that's already all I wanted to tell, so thank you for your attention.
So that's a comment. Your beautiful single, atom or ion implantation, and the possibility of using it for deterministic defects in silicon carbide, for instance, is very, very promising. I was not aware of that. This is yet another piece of the puzzle in which we can say, look, Helmholtz is on the forefront also for these things, because those materials are among the most promising currently in this field of defect centers, room temperature coherence. As you said, not only for computing but also for sensing. At the same time, I see that we do not have so much activity on this in Helmholtz in terms of quantum sensing. There's a little bit in Karlsruhe, as I understand, so there can be a connection there. But this is again a pointer that could be a pointer to other places in Germany in which you really have some substantial activity there. So that's a very, very fruitful one.
Thank you. I want to emphasize really, I was very brief in doing that. The Ion Beam Center having this low energy ion radiation, I think, is a unique facility. That's something that is built really new, not right now, and will be available soon. Of course, we have to find out how that works, how we can use that. So therefore, as I said, the long-term goal is really to have single.
But that's exactly what we want for our strategy. Yeah. So that's exactly saying, in 10 years we may be there, or in 5 years we may be there, and you will tell us what is the time, and where does it fit with other places, and what is the unique thing. So that I didn't know that we could cover with these unique features also the sensing corner. So that's fantastic.
So it's good that I was here.
Yes.
So we recall what you could lower energy?
Am I wrong? It's about really a few 100 electron volts or something like that. So it's really low. It's less, much lower than usual. Of course, you have seen there's a connection then a really high energy with the GSI, but here we are really lower as we have usually. It's not focused ion beam or something like that. That's already high energy. It will go down to really low, that you really have very low ions coming and implanting at the right position.
So, if you have to make a comprehensive strategy at the end, I think it is not so easy to explain the reader why Rossendorf stays in matter activity, while in Jülich and Berlin we move to information. I'm not recommending, I understand that you don't want to go another research field. All this is clear from technical reasons. But if you have to present to the ministry a strategy, it's actually not really clear.
Well, of course, always this question comes, and our answer is always the following. We are using user machines. These are machines where we have external users, and we want to do own research with these machines, and that is the thing which we are doing there.
Yeah, but we have the same argument, and Berlin has the same argument, but we don't use it. So
but that would mean, okay.
Yeah, I'm not saying you should do it, but I'm just saying if we need to have an answer somehow, which goes beyond this.
Or we should avoid the subject at all and just saying
it's translation.
But you know exactly what I mean.
Yeah, but that's a problem. I think that's a problem with Helmholtz in general.
solid, yeah.
They have to find some drawers where you are put in and to find the right ones. And the large-scale facilities, the only thing is to go to metric. That's the point.
No, it's always the same thing. If we are all separated, we say, why are we all together? And all together, we say, why is not a translation?
It's all exactly.
So here we do it differently. Somebody will come behind it, I hope not, but if we need an answer.
No, but that is really, we go offensive on with this question. We always say, okay, we do our own in-house research. I just did explain our in-house research. I did not go too much into details in the machine, of course. So if you count the FTEs which are involved in these activities, they are not so many. Many of the FTEs are actually involved in running LK2 facility. And that is on top of that in-house research. You know, there was a question, okay, you have these nice machines and you provide excellent support, but what are you doing on science side? Then you have to,
But it is the same for Berlin.
yeah, I know. So they decided just to go to a different Forschungsbereich, yeah, I agree. But we are working so closely together, I have to say, although we are in completely different Forschungsbereiche, and it's really a fruitful cooperation. Actually, the first slide Oliver Rader was showing, that was a cooperation done with Thomas Hanersdorf and Bella Lake.
But I mean, we don't need to convince us. We are
No.
convinced it's working good. We need to
We have
convince
to-
those who
yeah,
read
we
it
have to
and find
find
it
how to
a
sell
little
that.
strange. So here it may help that we also, when we write the proposals, that we make a remark that activities
Yeah, of course.
are the others adding,
Of course.
are the others, so that at least if somebody checks the document, that he sees that we work together.
But of course, for the quantum technology, we don't have to mention what Forschungsbereich we are.
Well, no, we should. I think we should. I think it helps.
Oh, okay.
Because if we show that this is going across Forschungsbereiche,
Okay.
this is even better. So that's just
Yeah, of course.
cool. You know, I like it.
Yeah, but
The system is why these people are all level. So if there are no quantum technology behind.
yeah, okay,
Oh,
but
no. I mean, come on. This is what I'm putting together. Okay, next time. Okay,
Yeah.
so that's exactly the point.
That's your
yeah.
answer.
That's exactly the point. In 7 years.
+2.
Yeah, whatever. Next round, not this one. Okay.
I'd be curious to learn a little bit more about the colors of silicon.
Just to go, you should answer that.
It's like a center.
There are some backup slides. I will provide it. Maybe you find some more information on this references there.
Very good. So now, thanks. And we are only missing David.
I'm coming completely from the application side in high energy physics and what drives us, and then coming from theory, doing lattice gate theories. And what drives me or what drives us are really fundamental problems that we have in nature, namely what happened at known zero baryon density, which means what happened really at the early universe. Why is there more matter than antimatter? Why do we exist? How are real-time evolutions, for example, in heavy ion collisions? How does this work? And how do actually collisions work in general? And in lattice gate theory, we have done wonderful jobs. We have computed a complete low-lying baryon spectrum from first principles. We can compute form factors, the inner structure of hadrons. But these fundamental questions that I just told you is inaccessible to us by all means. And the only way I see in the future to solve these problems is quantum computing, because I'm not aware of any classical methods that could address and solve these questions. Perfect. So I'm coming from any page one, please.
Need a hammer to do that.
What kind of steam machine is
Not a quantum computer.
that? Not this, obviously not a quantum computer.
I think this is again something that we rented from these people. Right?
No.
Oh, no,
It's our,
Worse.
Okay, okay.
It's our, it's our for modules.
Oh, okay.
Doesn't matter. I can remember my slides. So I'm coming from DESI. So we are also running large-scale facilities. We have a lot of X-ray sources. We have the XFEL. We have Flash. We have Petra 3, planning Petra 4. You are at the very end. And we have telescope arrays. And why do I mention this here? I mention this here because I'm convinced that also in these areas here, we have potential applications for quantum computing. These experiments are flooded with data. They do not know what to do with the data, and they are lacking computing. And here really, there are two things necessary: data compression and pattern recognition, where quantum computing could really help. So this could be potential extremely strong application. We are also guiding telescope arrays, and there are a number of theoretical papers that say we can really do these telescope arrays with quantum computing to coordinate this. And we have a strong theory group covering really a lot of things, and they are also quantum. I myself, to introduce me, I'm coming from the John von Neumann Institute for Computing, which is already a cooperation between 3 Helmholtz centers, Jülich, DESI, and the GSI. We feature 5 groups: computational biophysics, structural biology, particle physics. I'm coming from lattice QCD and nuclear matter. And I think these are again all application areas for potential need for quantum computing. And we have the connection already. Now, for DESI, quantum computing is still pretty new. But we had, in August, we had a workshop in Vancouver with Triumph. And there, we made a cooperation treaty with Triumph, E-Wave, and 1Q. And I read this in German. So we wanted to strengthen die Zusammenarbeit zwischen deutschen und kanadischen Organisationen, um die Anwendungsmöglichkeiten in den Bereichen Large-Scale Computing, Big Data, Machine Learning, and Quantum Computing to build this up. So this cooperation treaty exists. We are building up presently these working groups in these different areas. There are no concrete measures yet, but I think you should be aware of this cooperation and this interaction with Canada. Now here's my example. I did the work together with Tobias Hartung. The primary goal was to give a mathematical meaning to Feynman's trace formula. This is not important for you, but once we did this, we found that if we want to bring this mathematical meaning into practice, we needed quantum computing already. There was no other mean to do this. So we took an example, the ground state energy of a one-dimensional hydrogen atom, and we used Rigetti's 8-qubit Agave chip to do this. What we did, we performed a variational quantum simulation, and as I said, for this example already, quantum computing was essential. I would not have known how to do this in a different way. Now, we were very optimistic. We said we tried this out in the simulator without noise, and we found really an exponentially fast convergence to the desired ground state energy. That's the dream situation. The practice was, when we do this on a single qubit, then we found these fidelities, and the ground state energy was only given to 5%. So that's reality at the moment. And if we used more qubits, we could not achieve any significant result.
Are you trying to do this on an ion trap in quantum computing? So then you have higher tech.
I think I cannot convince Rainer Blatt or Peter Zoller to do this on an ion chip, but if you have needs...
Why not? I mean, you have this QT plan thing with Simone is coordinating, Rainer is there. I mean, you should really be studying this to them in that context. It's not that exclusively, but what does it matter? I mean, you think
So
you cannot
Rainer's
convince them?
right.
I think you can. I mean, this is among the things that they are most. Have you tried to talk to them about this?
I sent Peter the draft of this paper, but I think he didn't realize what happened here.
No, that's right. That's right. Yes.
We didn't realize that this is really something dramatic what we found here. We meant to find the Minkowski space continuum regularization of Feynman's trace formula. This is unique, the first time in history that this would be achieved. And therefore we can solve such problems.
Yes, so that's
But
a
okay,
major thing.
I think we should talk about this prime.
Oh yes, absolutely.
Yeah.
Sorry, and wow.
You
Okay.
are enthusiastic.
Wow.
I'm glad.
But then these results justify many approaches that we simply don't.
Absolutely. Yeah. No, this is really. This has not been realized yet that this is really a breakthrough.
No, come on. I mean, this is
And-
quantum supremacy. If you do it with 20 qubits, or if this is quantum supremacy not for a useless problem. This is beyond. This is sweeping away Google. Do you see that?
Yeah, of course I see that. I need the quantum computer that can do this.
No, but Rainer has it. I mean, no, we really need to talk.
But then I have another question. Why don't you do it on a bigger simulator?
Exactly.
You can simulate
Yes,
it.
absolutely. Yes. That's a good question.
With noise, you mean, or
No, she has
Yeah,
it
you
without.
can with noise, but also without. You can start without, but bigger.
yeah, but you see, I'm already here at the 10 to the minus 10 level. I have exponential convergence.
No, but the thing is that with her toy, you can do it with the
You can also
47
have
bit race.
noise. If you want to have noise, you can have noise.
I normally don't like noise, but okay, we can do it. So that's our example. And if you could help me, yeah, sure, I'm completely open and you are interested. No,
This
that's
is uber cool, really.
yeah, I know. I know. Thank you that you realize.
No,
So actually, I want you to look at it with the simulator.
yes,
We do
well,
it.
you must do that.
So, did you try the idea?
No, we didn't yet
No,
try
that's
the
too
IBM.
noisy. I mean,
From this example, I would think this is also still too noisy.
yeah.
This is I'm not I mean, we could try. This would be easy to rewrite.
No, this is actually a use case for unique, as a matter of fact, right? And then it's actually a use case because you go there and you try to in your modular thing with all the different platforms, and then even the MBA could buy it.
I would be most happy to.
Sorry, maybe could you just share your excitement? So,
Yeah, so
I would like to see the touching is going
Yes,
on.
yes, I can
What's
do
the
this.
breakthrough there?
What's the breakthrough? So this is a formula that Feynman wrote down like 40 years ago, right? And he said this trace formula, so this is the Hamiltonian, and he said I have to take a trace over the time evolution operator e to the IHT. I put in my observable and I have to normalize it with the trace e to the IHT. This expression here,
Sorry, is there the reason that 1t is large? No, it's just misprint, I guess.
that's a misprint, thank you. That's a misprint.
Expectation value.
That's the expectation value of an observable, for example, is can be the proton mass. And this expression here is completely formal. So this is completely undefined. And you cannot use it in any simulation because it is a Minkowski space. So you would have high oscillations. You would get never any result. Okay. So the only way to make sense out of this would be to do either perturbation theory analytically, but there you are restricted to perturbation theory, or to change to Euclidean time. And then you have here a minus instead of the I. And then this is well defined. You discretize the system, and this is what we do in lattice QCD. So what we showed here in this work with Tobias, if I do a zeta regularization of this object here, then this expectation value here is really the physical expectation value that you are interested in. That would be the same expectation value as you would get from a lattice QCD calculation taking the continuum limit. This we proved in this paper mathematically, and this was the prime goal. But then we wanted to have a demonstration that it works. And therefore we went to a very simple example here, and then we found this theoretical result and then this practical. But this would really allow you, if you have Minkowski space problems in the continuum, to regulate it and do a quantum simulation of that system. Shall I continue?
Yes, please. I'm completely shocked.
I think Ignazio was.
Yes, huh?
I think Ignazio was also shocked when we told
No,
him.
no, yes, no, of course. No, I mean, people, this can be, so this is one thing, so Google is running workshops, and trying to, and hiring people to find something of this sort which they have not found, okay? Because this is, I mean, this idea of quantum supremacy is you have some task which you cannot do with a classical computer, and now they have one which is completely useless, which is the random sampling of a random distribution of unitary matrices, and this is a useful thing. It is almost too good to be true. I mean, I think I'm dreaming.
And also from the particle physics point of view, it's very good.
Exactly.
Going to Euclidean space with what you said with the minus I is you buy in a lot of problems by doing that.
Yeah, sure.
So also from
Yes.
that point of view, it's very good.
No, but Ryan must do it. I mean, let's call him afterwards. Okay. No, I mean, yes. Okay. Well, okay. Go ahead.
I didn't expect such a reaction. Can I still continue? Okay, so this was our example. The status for me or for us is, so we could convince Rigetti to have a research partnership with them. So we have access to their new line of chips up to 128 qubits. This is granted by them. I have a research partnership with IBM Q. I have several hundred hours there and can run there. There is a strong collaboration with the Institute for Quantum Computing in Waterloo. Then we have collaboration with Tobias at King's College. And as Thomas already mentioned, we are part of the European Quantum Flagship, which is Quantum Technologies for Lattice Gate Series, QT-FLAG. And within this collaboration, we have also very close contact to the group in Innsbruck and other groups who do really optical lattices and quantum simulations there. And our ideas are to really have applications at the moment in lattice gate theory, but this also reflects a lot of condensed matter physics and perform computations that are not possible otherwise. And I told you already, these are the very early universe with non-zero baryon density, the matter-antimatter symmetry, real-time simulations, and so on. And one idea I had, but this is of course here anchored very much, but I had this for DAISY to build the quantum computer, and at least the people at DAISY did not laugh at me. So, so there could be an idea because they have of course a lot of expertise in cooling and shielding there. So this could be maybe one point of collaboration. The prospects are, of course, we need better fidelities. So we need to develop further cooperation with companies, and I emphasize this also with experiments in the lab, because the techniques to optimize these simulations are the same, whether you do it on optical lattices or on these chips, and this can only work together and we can help each other. And we need better optimizers for variation quantum simulations. This is desperately needed, and this needs in particular a close collaboration with applied mathematicians. And there we have already quite some connection. And our idea is to tackle gate theories in high energy physics models with increasing complexity, pure gate theories, coupling fermionic and bosonic matter at terms that have design problems and perform real-time dynamics to reach finally a lattice QCD corresponding lattice. And this program here has been submitted together with Christina Muschig as co-directors to a large Canadian CFA proposal, which is evaluated at this particular moment. And I think this brings together really a world expertise from high energy physics, quantum information, superconducting qubits, and also optical lattices experiments. And if this works, I think we have here a very strong component that we can also bring into the Helmholtz function. And also what I learned last Monday and Tuesday, I think we really should explore possibilities of quantum computing for experiments. This is heavily discussed at CERN at the moment. They really want to do something. They want to watch the field of quantum computing for experiment. And again, the topics are pattern recognition and also data compression. This is for them very, very important. And they are looking into this, and they're trying to build up connections and collaborations. Yeah, and essentially we have to look for the new generations of quantum chips, also the ones that are blend here. And also, we should not forget we have to do software and algorithm developments. And we shouldn't forget the laboratories. So that's my perspective on this.
So I have two comments. I have many comments, but two are relevant. So they mentioned to you yesterday night the European Commission called me and they said that now we have to set up a sort of large-scale brainstorming and for collaboration with Canada, between Europe and Canada. And so this, I think, should be a very important and central piece of it. Yeah, obviously.
This is there.
Exactly, it's there. So we should build on it. And second, I view this as a very clear, as I said, a clear use case for unique. Yeah, which is this idea of having different quantum machines located in Munich for applications in different directions, and which has been going through back and forth for different reasons with the NDF. And yesterday they told me that now they want to see how it is embedded in the whole strategy, and this is really something that would even require that.
Absolutely.
So and vice versa. So it would be a mutual benefit, which is kind of quite evident, and so just go for it. And this is really the context to develop that.
And I will answer the question you didn't ask, namely, what is missing here? What is missing here is really the access to quantum devices, where we can test ideas, where we can develop algorithms, where we can play with these optimizers. I mean, the present methods, they will not work if you have 10,000 qubits. The number of parameters would just be too large. There has to be substantial effort here to make this practical in the future. And this I really need, and this is very, very important.
I think regarding the idea of building a quantum computer, we have some expertise that is lacking in our institute where the quantum physicists doing a large-scale project by
Yeah, I think for sure this has to be coordinated. I think in particular this has to be coordinated with the plans at CERN, right? Because what CERN is offering, they have something that is called Open Lab. And with Open Lab, so they have really fixed agreements with many, many companies, DWave, IBM, Rigetti, Google, Microsoft, you name it. And what they want to do is to give access to these companies through their Open Lab strategy. And so this has to be coordinated in some way.
That's the application side.
Yeah.
Budget.
But there could.
And that's something that us public sector is basically not used to.
That's a very good point. Thank you. Thank you. I will bring this forward.
Yes.
So, if you like, you could also take your questions to the coffee break. If there is nothing which is not pressing for you now, which everybody needs to hear, no? Then we have, because we are a bit late now, 20-minute coffee break.
Das ist